There are a lot of properties in the real numbers that we're used to working with. Some of them make sense, like the commutative property addition. 3 plus 5 is the same as if you did 5 plus 3. Well, there is a commutative property for addition for matrices as well. The order of the matrices that you add together does not matter. The associative property also exists. Remember, that is, if you had 3 plus 4 plus 5, you could decide to add the 3 and 4 together first, or you could add together the 5 and the 4. You'll still get the same result. That also works for matrix addition. Here they have, so those two you're pretty familiar with. The next ones are like the super duper distribution. You can distribute across multiple matrices with a scalar on the left or the right hand side. So that's like if you had 3 times x plus 1, it could give you 3x plus 3. That is a totally fine and normal operation that we're used to dealing with. The equivalent for the right side would be x plus 1 times 3. And even when you distribute that through, you can see you still get the same value. So the side that the scalar is on does not matter. We are limited in them. I wanted to point out, to make sure you saw it, not all are true. So there are some properties we'll talk about in later videos where what we're used to happening doesn't work anymore. But these 4 do work. Let's go ahead and apply some of that to an example here. So we have 2 matrices, A and B, and we're going to find the expression negative 4 times matrix B minus 3 times the matrix A. Well, let's write that down. Negative 4 is my scalar. Negative 4 is my scalar. And matrix B is negative 4, 2, and negative 8, negative 3, read by columns. Subtract 3. See, it's really hard for me to not write it on the line there. Negative 3 times the matrix A, which is negative 9, 2, 12, negative 6, read by columns. So now what we're going to do is we're going to distribute those scalars through, do our scalar multiplication. Negative 4 times negative 4 is positive 16. Negative 4 times 2 is negative 8. Negative 4 times negative 8 is positive 32. And negative 4 times negative 3 is positive 12. And now we're going to add our other matrix in. And the reason why I'm making it addition is because I'm multiplying a negative 3 through everything. You could keep this a subtraction and make it a multiply by positive 3 each time, but I find it's easier just to do the whole part here, negative 3, keep it like it is. Negative 3 times negative 9 is positive 27. Negative 3 times 2 is negative 6. Negative 3 times 12 is negative 36. And negative 3 times negative 6 is 18. Now that we're down to just the matrices, what I'm able to do is add them together. So I add them positionally. 16 plus 27 and negative 8 plus negative 6 for my first column. 32 plus negative 36 and 12 plus 18 for my second column. And we simplify that out. 37 is 43 and negative 14 for my first row, and negative 4, 20, 30 for my second row. So I get it down to one matrix that is the same dimensions as the original matrices A and B. And that's always a good check. When you're adding or subtracting the matrices, it should be the same size when you're all done, dimension-wise, as what you started with.